Hello and welcome to Cambridge Skeptics Live. Cambridge Skeptics are a not-for-profit education organisation for the promotion of positive skepticism, critical thinking and science in the Cambridgeshire area and beyond. And tonight I am strangely excited about the prospect of learning all about p-hacking from our resident statisticians, Sam and Erika. So I will hand straight over to them so they can get started.
Thank you for the warning, the content warning on this. It does contain spreadsheets, and it might get really, really exciting.
Were you just cooling yourself down there?
Yeah, no, yeah. I'm getting
just that excited by the spreadsheets.
I just really love spreadsheets. Sam's like, yeah.
Yeah, of course.
I wanted to ask you guys before we get started is, do you have a working definition in your head around the term p-hacking? Do you know what we're referring to when we talk about that?
Yes, sort of.
Yeah.
But it's basically finding positive results from data that might not necessarily support it, sort of thing.
That's a really good definition. Yeah.
It's 100%, or rather, it definitely sits in the field of statistical dark arts, but is also in the field of sort of desperately, well, it can be misguided as well as being malicious.
Yeah, and it's really interesting that like so much of what science and I think skepticism is trying to do is helping people overcome the biases in our thinking, so that we can make better decisions. And a lot of that is sort of formalized in the scientific method and in statistics. And it's interesting that despite the kind of the sort of like fundamentals of that, there's still ways that our psychology can trick us down these motivated reasoning routes that allow us to mathematically trick ourselves into thinking that there is a real pattern that we're seeing when it's in fact entirely due to random chance. And actually, I was asking Sam the other day, like if he, like what's the relationship between p-hacking and say some of the logical fallacies that we talk about at other times. I don't know, do you guys have an impression off the top of your head about what you think that relationship might be?
I guess confirmation bias would come into it.
Yeah.
I kind of want to say like a straw man fallacy in that you're sort of misrepresenting the actual argument with.
I
think
cherry picking.
Yeah, very much cherry picking.
Yeah. I think on the straw man one, I think there is definitely ways in which you can make the null hypothesis, the sort of the current status quo, a straw man whilst steel manning your own hypothesis. There is definitely an element of that, and cherry picking,
and also like generally motivated reasoning.
Well, that's it. That's it. It's numerical motivated reasoning.
Yeah, it's really like, and that's why this isn't like, although we love spreadsheets and data, we think that it's something worth working through for an audience of people who don't use that as their primary way of making decisions, because we think that it's a way of.
Do such people actually exist? Come on, let's be honest here. Who doesn't use a spreadsheet to make decisions?
I recently had a vaccine, and while I was getting the vaccine, I was talking to the nurse about how much I love vaccines, and she's like, "I know, right?" Like she had to go through a thing of like, "Do you understand what like the benefits of why you're getting this?" And I was like, "Oh, 100%, lady. You do not like I am pre-signed up for this." But yeah. So the reason why we think that it's worth going through this example, which does involve spreadsheets, is because it's a real life example about how it's so easy to make these logical fallacies happen in a real context. And yes, it's a thing that scientists are increasingly trying to learn how to avoid better. It also affects decisions that people can make with numbers in other areas. So both Sam and I in our day jobs, make decisions where we are always trying to counteract the effects of things that could be p-hacking in a business context. But even if you're not using numbers to make these kinds of decisions, the same critical thinking skills that you need to apply are the same sort of logical fallacies that we talk about all the time. So, the example. So, you guys have inherited a website, an online store from an old friend of yours. It's not a very pretty website, as you can see. The design is terrible. Oh, wait, can you make it full screen, actually?
Is this designed by the same people that did the Natural News website?
Let's just say
that
I am not an expert in e-commerce.
I don't know how you make stuff full screen in Google.
For me, it's on the top left.
I do like our project range,
right.
though. Shoes, umbrellas, popcorn, and gifts. That's
yes, it's a very random store. It has a variety of variety of weird items. You will note the font is Comic Sans. It's terrible.
Makes sense.
Yeah, exactly. So you guys have inherited this website from a friend of yours who, as you can tell, is quite conservative in his understanding of e-commerce design principles.
I'm worried he called his website Chris and Andrew's Awesome Online Store.
I think that was his final gift to you in giving you the website. He's like, right, listen,
just as he was dying.
Yeah, exactly. I don't want my name associated with this anymore. It's up to you guys now to carry it on. And so I assume that we're all familiar with how online stores work. You know, we've got a list of products that you can buy. When someone comes to the website, they can browse through this list of products. When they want to buy it, they click on the Buy Me button, and then the product goes into their shopping cart, and from there they can then pay for the item.
And then we start a space agency.
What was that?
I said, then we start a space agency. That seems to be the general trend.
Yeah, exactly. And
I think don't we make workers urinated bottles somewhere between those?
Yes, somewhere along the line.
Yeah.
I'm already doing that, so don't worry about it.
And like I will say that like actual online stores are perhaps like a little bit more complex. They might have additional sort of steps in here, but we're simplifying what's happening for the sake of.
More complex than this. Are you sure?
We have red shoes and blue shoes.
Yes.
They certainly have better font choices. I will say that. And so yeah, you guys have inherited this, and you're like, well, we definitely want to make this better. And there are obviously a lot of design problems with this. But Andrew, you have had this idea. You've been looking at the financial side of what's going on with this website. And you've been really focused on looking at the percentage of people who click on the Buy Me button every day. And this is really important because they can click, on other parts of the website all day long until the cows come home. But the only way that you guys can make money is if someone buys something. And the only way that people will buy something is if they click on that Buy Me button. There's no other way to start to get the item into the shopping cart and then for you guys, for the person to actually purchase. So you've done a bit of research and you've noticed that only 4% of the customers click on the Buy Me button. But you've had a look at some of your competitor websites and they're getting numbers like 5%. So you're like, okay, maybe there's a problem with the Buy Me button. So your idea, Andrew, it's a brilliant idea, is to make the button bright red. Yes. And as you can see, it's a revolution in design. It has vastly improved the experience for the customer.
Can we make it flash as well?
I think that would be an option. Yeah, because you can make it rainbow colored. But for the purposes of the mock-up that I have done here, I actually considered making it rainbow colored, but I couldn't work out an easy gradient for that in my presentation. So yeah, you decided to make it red. So Andrew, you go to Chris, you pitch this idea. Chris is on board. Yeah. and you decide that you want to test whether this is an improvement or not. So how are you going to test it? I think you know enough about like experimental design and things like that you can probably come up with a reasonable testing protocol, right?
Yeah, I mean, off the top of my head, I'm thinking, when someone goes to the website, it's randomly either black or red, and we record whether more people click when it's red than they do when it's black.
Yep.
Yep.
And are you going to, and I assume you want to kind of split 50% of people will see one, and 50% of people will see
50-50, so you evenly split between people who visit the website.
Bingo. So this is what we would call in science tends to get called a randomized control trial, or an RTC, or in the business world, it tends to get called A/B testing, because you're testing option A, the black version, versus option B, the red version. And theoretically, if we wanted to try a third option, like Chris's flashing option, we could do A, B, C, D. Test multiple options side by side, if we wanted to.
Yes.
So you set up the experiment, and you start collecting some data. And this is where Sam might start to take over and show us what some of that initial data looks like.
Well, so before the test starts, oh, that's wider. So before the test starts, performance is running along at about 4%, a little bit low, but that's just some random variation.
Can you tell us what the axis labels are? Because they're...
Yes, I can. So on the left-hand side, you have the sales rate, which was at 4%. Along the bottom, you have the day of the test. So each day, it summarizes what you have with each. Essentially, what the website does. And on the first 2 days, well, this black point here, trundling along at sort of 3.7%, but actually this red button here doing much better.
I think you may have to increase your zoom.
Better?
Yeah, that's better. Yeah, that's better.
Yeah.
What's the blue line, or is that just a? Oh, that's okay.
Well, so then I suppose the next question is, well, first question is, does that look better?
At a glance, yes.
Red is better, Chris?
Red is better than what? What's the other option?
The black line at the bottom.
Oh, the black line at the bottom. Oh,
Right.
yes. Red looks much better.
Yeah.
Okay.
We should stop testing immediately.
Yep. Let's stop. We're done. One day.
There you go.
I was right. Let's just call it that.
Yeah, and so obviously being a little bit facetious there, but if we continue the test on, actually those are the first 2 days. Oh, actually, that's it. And then it actually, you know what? After 5 days, it crosses over. Black's doing better, and then in this case, it trundles along to the point where actually there's no difference. They're exactly the same. And so you sort of hit one of the nails on the head there. There is a significant risk in stopping too soon.
And before you even make that decision, if you go back to the first day example, the first I think it's 2 days of the test. So I think the question that I was expecting Andrew or Chris to ask is, yes, red is better than black, but how do we know that that's real? And the answer...
It's on a chart.
Exactly. It's on a graph.
Well, no, okay, so maybe using the sciencey lingo, how do we know that that's significant?
Ah.
So as in, is there maths that we could do to guard against the outcome that we ended up seeing, which is that in fact it ended up just being due to random chance. And The answer is the kind of the basic statistical answer, the fundamental statistical answer, which is yes, there is, and that's what that blue line is telling us. And the question that I would ask you both is how often are you willing to be wrong?
I'm wrong all the time, so I'm very willing. Just ask Ellen, she'll tell you.
Right. So let's imagine that you.
I believe the science answer is 5%, isn't it?
Yes, exactly. The science answer. Scientists tend to go with 5%. Sam, are you going to say something?
Why is it 5%?
I don't think the reason is there.
Yeah, it's just a convention, really, isn't
it? It is literally just someone went, oh, that seems reasonable. Well, more or less. But why isn't it more than 5%? Why isn't it 1%?
Oh, that's not reasonable.
But why?
There is a trade-off.
Because it's 5%.
Well, but
okay. So you've got to get the balance between false positives and false negatives, I guess.
Well, yeah, and I think there's a question as to like, okay, you've got a fixed amount of data, but in this case, you could keep running this experiment for as long as it need, as long as you need in order to decide one way or the other. So, why would you want to choose 5% rather than 1% or rather than 10%?
Well,
I don't have an answer to that.
While you're thinking about that, let's go on the risk of the false positive, right? So the smaller the number, hope I got this right. The smaller the number, the less willing you are to be wrong. So you're going to have fewer false positives. Yeah, I know this is hard.
I guess it depends how important.
Yeah, so exactly. That's a good criteria.
If it's a life and death thing, you might want to set it a bit lower.
Exactly. Yeah. Or like if you are making a decision about whether or not you've detected a new particle that is going to fundamentally alter the laws of physics, you might want to be very, very, very sure that it's not due to instrumental error.
Yeah.
Whereas, and an example is also, in say like pharmaceuticals, the risks of being wrong can be really high, and so we can afford to have a trade-off so that we can be more sure about the result. There's another factor. So part of what affects our ability to so the confidence that we have that the two numbers are different from each other. Part of what affects that is the actual truth, right? Like, are the two populations genuinely differently? Mathematically, there's another factor that affects how well we can estimate that difference.
And I think there's an illustration of this, which is Andrew. How long do you think you'd have to know me in order to feel comfortable giving me a $5? If I asked for it.
I don't know. Probably not that long.
Okay.
No, I mean, yeah. Know a little bit about you.
What about your house?
Probably a little bit longer.
Yeah.
To be honest, if you want to swap, I'm good with that. You can have mine.
But here's the
I'll
question,
move in
Andrew.
yours.
Here's the question. What if you met Sam at a pub and he asked for a $5 and you gave it to him? What if then 10 years passed and he asked for your house? Would that be enough time?
Did he give the $5 back in those 10 years?
You've never seen him in between.
No.
No, why not? Why does the absolute amount of time not matter?
I think it's ultimately, obviously, the value of the thing, the importance of it.
But isn't it also that you haven't collected any additional information about Sam?
Oh yes. Okay, sorry.
Right?
Yeah.
You don't know anything more about him.
Yeah, the gap in between doesn't matter. It's before I'm going to give Sam something more than a $5, I'm going to want some more information.
Yeah.
On that.
And so mathematically, what's happening is the same thing statistically. Instead of more information, we need more data.
Yeah.
And how you can get more data, you can't. So one way to do it is if more people come to your website every day.
So a bigger
But if
sample size.
you could magically make more people come to your website every day, you'd be having different challenges, right? So instead, the trade-off that you have to make is that you let more time elapse. And that's often the trade-off that we end up making in science as well as in business, is are we willing to let the experiment run for longer so that we can get more data, so that we can be more confident about the decision? Or is it better to make a decision faster that we're less sure about? And Sam has a nice figure that explains this.
Yes. So in this case, it's a balance between three different things, which is your willingness to be wrong, the amount of data that you're collecting, and then also the actual size of the difference between the two different options that you're testing.
Right.
So here we've essentially got three different sort of variables. How much data we're collecting on a given day, what the difference is in this hypothetical. Let's say the red button, has a 5% sales rate rather than 4% sales rate, and then also actually how sort of what level of confidence we want to be, what we want to have. And so if we were to change this, at the moment it takes us 10 days to get to 85%. Well, actually, if we were to make this 200 a day, suddenly it becomes 5 days. Or alternatively, what if the size of the difference actually is significantly smaller? Well, it takes us much longer. To a point where actually I need to extend my table. Yeah. And so, it's a matter of what's the cost, what's the harm if you get it wrong, and actually how feasible the experiment is. How much data you're going to collect, how much it's going to cost you. In my own job, we build that set the price, and we have a testing period. But actually, if we build a model every year, if we're going to test it for then a year and a half, that doesn't make any sense. We're not going to roll it out one way or the other before we've actually started the next one. And so we're more willing to be wrong because of the lost opportunity cost of not rolling out the model.
And also, no one's going to die.
And no one's going to die
if we're wrong, which is like legitimately a factor. Like it's thinking about the consequences of being wrong helps decide where to put that. So for you guys, this whole statistical sort of trade-off thing, this is part of the basic statistics that we do before we even talk about the fallacy that we've fallen into of stopping early when the result was favorable. So we've done these basic statistics, and it looks like we have I think it's a 75% chance of being right. That's what the blue line is saying at this point.
76.6.
Yeah.
And actually, in the chat, Sheldon has said, look at the first chart and see if it's varied more than that difference. That is a good rule of thumb measure. Is actually look at the field of general entries and then ask, well, actually, how does this sit within it? If it sits relatively close to the center, likelihood is it's not going to be a significant difference. If it sits well outside of the range, likelihood it is going to be significant. And if it's somewhere in between, then you obviously, you always need to collect more data. But as a good thumb.
Although an interesting additional challenge in the kind of website e-commerce world is that if this was an experiment, say, of people coming into a lab or a more controlled system, we would have an a priori reason to assume that any given day of the test would be similar to any other day. However, we know in terms of people's behaviors, in terms of online shopping, that there's really good reasons why someone's shopping behavior on a Friday night might be very different from on a Tuesday morning. And there might be other factors like what if it's the period leading up to Christmas and things like that. So, and we call all of this seasonality. And so it's another reason why we might, even though say we have day 1, day 2, day 3 of the test, we might, because we know that there can be higher, week on week variability, we might want that test to run for longer so that we can capture things that are not even being seen in the statistics.
Yeah. So you want a good representation of the whatever cyclic, seasonal effects are in play.
Mm-hmm. So if you guys were comfortable with being wrong 3/4 of the time, you might have said, yeah, let's go with the red test on day 2, and you'd have a 75% chance of being wrong based on those statistics that we said.
Well, or are they?
Exactly. Or sorry, being right. 75% chance of being right. Sorry, I got the words wrong.
So then, well, no. So there's then within, and this also, I suppose, isn't. It kind of is p hacking, but it's definitely within the realm of bad statistics and sort of Jason if it's not p hacking. But if I perform a test and on day 1 it's negative, and I've set myself, let's say, a relatively high rate, 95% significance, and then I perform the test again on the 2nd day, and then I perform it on the 3rd day, the 4th day, the 5th day, the 6th day, and the 7th day, how, does that impact the quality of the test versus just performing it on the 7th day?
Well, actually, Sam, would it be fair to ask the question, tell me if this is right, is how many experiments have you run?
Yes, that's another question.
Yeah, how many experiments have you run?
If you test every day up to the 7th day or just on the 7th day.
Is the answer
okay, so you run 7 tests on the first version and only 1 test on the second version. Okay.
That's mathematically what's happening statistically.
Right.
So if you if you check on the first day and you'll intervene.
Yeah.
If it's a fail, if it's a success on the first day, and then you test it again on the 2nd day, and then the 3rd and 4th, 5th, the 6th, and the 7th, your significance, your confidence is not going to be 95%. It's going to be 70%. You do that for 2 weeks, you're at 50%. Continually testing is more likely to produce a false positive because all you need is a little bit of randomness to take you above the line.
Yeah.
Once.
Yeah, which is what's happening here.
Yeah, that's what happened on this 2nd day. There was just enough to get you over the line if you, in this case, doing 75%.
And Sam, did we say what the truth? So these are obviously simulated data. Did we say what the truth is?
They are both completely random with identical parameters. There should be, given long enough time, they should be exactly identical. Which is
Andrew, you look like we've tricked you, and you're upset.
No. My brain is going.
It's been
a long day at work. Are you following this at all?
So this is an example of p hacking.
Yeah.
Where and I think Sam has explained the math of it well. What's happening is that the confidence that we can have in our test actually gets much lower every time we do multiple tests.
Yeah.
And that's a known statistical fact. The reason why it becomes p hacking is because it's really easy to fall into this trap of stopping the experiment early when we get the answer that we want. And so that's why it's an example of the kind of the logical fallacy type thinking.
Is the sort of the opposite also true of keeping the test going until you get the answer you want?
Yeah, it works both ways because stopping early, like if you allow yourself to decide on any given, let's say, day, whether the results are adequate or not, if you're giving yourself that choice, effectively every day becomes a new experiment.
I know that.
Even if it's using the cumulative data from previous days.
I had this similar sort of thing when I was doing my psychology thing with participants. It was like, you have to say to start with, this is how many participants I'm going to aim to get.
Exactly.
I'm not going to go, I didn't get my results with that. I'm going to do another 50. And, Yeah.
Because then you're just testing until, like, if you're going to keep testing until you hit significance, you're guaranteed to get a significant result.
I know this is something that comes up a lot in ESP experiments where they go, oh, he must have got tired at that point because he starts getting wrong answers.
Yeah.
Yeah, but that is cherry picking, and obviously removing the incorrect answers is a key part of p-hacking, which is erroneous outlier.
Yeah.
Or
Which
sampling.
maybe we want to segue to that example.
Yeah, let's segue to that example.
In the meantime, while you set that up, I can tell you, like, maybe I'm thinking of some examples of how early stopping or of an experiment might be used for people like in a non-mathematical context. And I'm thinking, like, you know, it could be something like, I want to see if driving with my, you know, my windows down gives me better mileage, or I want to see if, you know, this you know, putting my child to bed earlier results in less crying the next day. And potentially what someone can do if they have motivated reasoning around that is they can, you know, and then they might say, okay, I'll try it one day, I'll try it the next day, or like, I'll try it for a 2-week period and see what happens. And they might either say like, well, I had 3 bad days in a row, therefore it can't work. Or they might say, okay, yeah, so we finally got to the point where it's working. Let's continue on. And I think in situations where there's a lot of like very subjective variability, it's really easy for people to go with their motivated reasoning around whatever it is. And in situations where, you know, like especially around like kind of like lifestyle decisions or like child raising decisions, if there was really, really good data about stuff, we would know about it. So much of it is like subjective and idiosyncratic. And what I'm not saying is that people need to like do complicated statistics around their lifestyle choices, but rather be aware of how stopping an experiment early because it either is consistent or, you know, because especially if it's consistent with something that you were hoping for, might be an example of motivated reasoning in your daily life. So we were talking about outliers.
Yes, so we have this particular version of the test. Andrew proposed it. It's set up after 3 days. He was like, yep, you know what, roaring success, I'm going on holiday. Chris, can you just keep running it until we're absolutely certain? And Chris, being the vindictive business partner that he is has sort of, you know, managing this thing. And, you know, you're getting towards the end, you're like, oh, come on, if you could just get over. Andrew's obviously been taking a really long holiday at this point. And so Chris is going through and he goes, oh, actually, no.
I earned it. I changed the colour of that button. Come on.
Day 26 of this test. Now, we know that Sheila in accounting sneezed on the server, and that probably had a bit of an impact. And you know what? You don't like that. I'm just going to get rid of it.
And that was that day. What was the day on the graph before?
In that day, red did really well. Black did kind of badly. You know what? That's.
And where is it?
In the interests of the experiment, because I want to show Andrew up.
Okay, cool. I'm just asking.
Oh no! Get rid of that day.
Yeah.
And then, actually, we know that. Let's see. Oh yeah, actually, yeah. You know what, Sheila, she farted near it this time. In any case, get rid of that. And actually, we know that there was a shoe sale on at this competing firm, so let's just get rid of that day as well. Is that enough? Yeah, 95.7%. That's enough. That's 95% significance. We're calling it. Mic drop. Yeah.
Beautiful.
3 or 4 days, and you're done. And so Andrew comes back on day 80, and Chris gives him the bad news.
All that work I put in.
Also, I will say that we deliberately set up some motivated reasoning for each of you in this fake scenario. We don't actually think that you're vindictive, competitive, adversarial people.
I love Sheila. She's great.
It's all Sheila's fault.
It's all Sheila. Gassy Sheila.
And so in this case, whilst there does have to be a bit of actual scientific literacy and common sense applied to the results you get, there is obviously this risk of motivated reasoning of twisting your data to suit your theories rather than your theories to suit your data, and so there, I would just say that as scientists, you'd have a really, really high bar and a good rationale for why you're removing data. There can be perfectly reasonable reasons to.
Well, I was going to say, so I had like an outlier elimination sort of protocol when I was doing science. And the science that I was doing was I was taking small bits of protein from or like other organic material from archaeological sites, and I was measuring some of the chemistry from that. In order to do that, I had to do sort of some lab chemistry ahead of it, and then I had to put the piece of material that I got out that was sort of purified into a machine, and it was like this like little like dispenser thing, and it would drop my sample down. It would incinerate it at 1,000 degrees. That then would get turned into gas, which would get ionized, like a charge would get applied to it. And then it would get fired down a stream of, I think it was helium gas, something inert. And it would get put around a corner by a magnet. And then around having gone around the corner, that would separate out the different weights.
Okay, this is sounding like a Rube Goldberg machine.
I know. It was it would separate into different weights, and it would
trap the mouse.
Particles would hit a little detector, and the detector would detect the electrical charge and count that as one particle. And what I do then is you measure the total amount of charge collected by one cup versus the total amount of charge collected by the other cup. And that was the number that I was looking for. I was looking for the ratio between the two. And the reason why I'm going into all that complexity is because there's a bunch of steps happening inside this machine. I can't see inside the machine. All I can see is the electricity being measured at the end in different things. I can and so I had, but sorry, on top of that, there are legitimate things that can go wrong in that process. For example, I mentioned this little like tiny, like sort of carousel dispenser thing. I would have like 100 samples at a time in these little tiny tinfoil balls. And the dispenser could sometimes jam. Sometimes it would fail to drop a sample. Sometimes 2 samples would drop at once. Sometimes it would fail to combust correctly, and that could happen like if the chemicals needed to be changed in the machine, or like some of the supplies needed to be changed. And so I had to have a way of distinguishing, genuine outliers that were caused by a machine malfunction from like, wow, that cow sure had a weird diet. Which was the sort of thing that I would be saying back in those days. And I remember like specifically, I had a cow that had a really weird diet in Bronze Age Greece. So what I would do in my protocol is I would check every single value. I would check all of the sort of experimentation values for every single thing. They were all within range. And on top of that, the value that I was measuring in this cow was biologically possible. It wasn't like it was from the moon or something. And so, the conclusion that I came to was that we have to assume that this is a genuine result.
Just a weird cow.
Just a cow eating a bunch of seaweed. Grazing on the coast.
And so, in our example... What?
Normally when I come in with examples, they're to help make it more relatable. My example is 100% less relatable than our actual example.
So in our case,
I think I showed people magic tricks. So that was what I did.
Well, in our case, Sheila went out for 3 days
to go see a
promoted-
doctor.
Irritable bowel or something.
Sheila's the only
It's probably
other
a diet of
you have,
seaweed she's
okay?
on.
Like it's just Andrew, Chris, and Sheila. Poor Sheila's doing all of the work, and these two guys are just talking about button colours. Anyway, she goes out and she goes to a colourblind conference and promotes the website. Now, of course, if you're at a colourblind conference, likelihood is that whatever impact, whatever data you collect over that period of time, when the colourblind people are coming to the website, is not going to be very useful in terms of this experiment as to whether red or black generally works on, I don't know, chromonormative people.
Sounds like a word.
And so these 3 days where you have double the normal number of volume and very little variation, that would be an appropriate outlier removal.
And to be honest, you and Sheila really should have synced up, because
I'm not sure why we sent Sheila to this conference, to be honest.
Yeah, specifically around color, and she goes to the color blindness conference in order to promote the website.
I think Andrew's just gone on an 80-day holiday. Oh, he's back.
Yeah, I'm back. I lost you. I didn't hear anything you just said then.
Don't worry, we're making fun of you.
I was just being vindictive about you.
Yeah, I was just off on holiday again, like you said.
And Sheila on for a couple of seconds.
Yeah, I had to deal with her. She's just, God, dear me, trouble with her guts again. But,
Stop eating seaweed.
yeah, exactly.
So is that everything that we wanted to say about outliers? Basically, sometimes they're legitimate, sometimes they're not legitimate. The main thing is that you need to, I think, what I would recommend is that you need to decide ahead of time when an outlier will or will not be legitimate, and how that might affect your everyday life is again, sorry, all of my scenarios are childcare related. That's just what I've been researching lately. But let's say you're doing this experiment around child going to bedtime, and does that improve crying? If the child has a cold, that might be a reason to discontinue the experiment for that period. Although, however, my understanding is that children get 6 colds a year on average in the winter months.
So you'd have to try and work out all these possible reasons for outliers at the beginning.
Yeah, a bit like Andrew's example where it was, no, you have to figure out how many people you're going to view at the beginning.
Yeah.
You also have to set your criteria for outlier removal. It's essentially, all these things are about trying to remove your own motivated reasoning by making the decision before you can see the results. Because as soon as you get to a point where you start seeing the results, your brain just goes, oh, well, actually, maybe it'd be a little bit better if I was just a little stricter or a little more lenient on this thing or that thing. By setting it beforehand, you can ensure at least a measure of impartiality.
But aren't there going to be things you couldn't possibly predict that still deserve to be removed?
Yeah, potentially. And you'd have to think really, really hard about whether that invalidates your entire experiment.
Right.
Yeah, which is why you need to kind of have a really high bar for setting any new criteria.
Yeah.
For example, a war. Pretty much any experiment having a war would make it difficult to continue.
Yeah, exactly.
Yeah.
So that was outliers. There's another really commonly, and this I think is possibly our last example. Another sort of, exactly this one. Another trap that you guys might fall into. And actually, Sam, could you go back to the storefront for a second, because I think that might be might help explain it a bit better. So we're in this scenario where Andrew really, really, really wants his red button to
A lot of
be
effort
right.
to that.
Yeah. So far, despite his attempts at stopping the experiment early, we've had Sam the statistician come in and give him advice, and so we've determined that no, that you've done the statistics wrong there. The results seem to be inconclusive. Chris tried to do some sketchy outlier removal. to make black the winner. But that also Sam, slapped his wrist away from the keyboard and was like, "Stop that." It turns out that Sheila's colorblindness conference, as expected, had no impact on the test, but it was good to remove that just in case. So Andrew has one more go at this, which is he said, okay, well, maybe the red button only works for some types of products and not others. And so what we have on the other slide is an example of what that data looks like for some products and not others.
Yeah, and so top left, we've got all the products together, but by subdividing it, yeah, you get some that don't really seem to have any difference, but you get others that are looking mighty fine, at least to begin with. Or this one that tends to do stronger towards the end. And this is, broadly speaking, another manifestation of that testing every single day versus testing at the end.
Yeah, you've done 7 tests instead of 1 again.
Well, 8 in this case.
But yes, yeah, by testing it lots of times and by not correcting it in the process, it's just allowing you to kind of massage and maneuver. And actually, to a certain extent, the tests themselves are almost this form of this optimal stopping thing, where if you keep massaging and redoing tests until you get a success, it's you could in theory just keep subdividing and subdividing. Okay, it's not food, it's specifically popcorn versus hot dogs versus whatever. If you keep subdividing enough, you will eventually find a significant result.
And this is a trap that is so easy to fall into.
Yeah.
And especially when there's the motivated reasoning is strong, and people are seeing inconclusive results. I see it a lot. People really, really, really want to find something. It happens, I think, in life. It happens in business. It happens in science. People really want to see a significant result. And what I would always, so like Sam said, is that we can control for this if in the math, as long as we pre-declare ahead of time how many of these comparisons we're going to be. Let's say
Bon fucking fruity.
Now we're going to have an 18 plus tag on this.
No, it's all, I've already put it up as it's not safe, not good for children. Not okay for
Kids love statistics. What are you doing?
Yeah.
Yeah, okay, thank you, Chris. Thank you for bringing me back down to earth. It's not a bunch of kids anyway.
So I did tags for this, so just like half the tags are all about Bonferroni.
They are, but I was looking at them today.
I went and Googled Bonferroni because I saw how much you tagged it.
It's literally like the first thing I learned in my job was just like, okay, did you do Bonferroni correction at uni? I'm like, yeah. Like, no, go away, learn it, because otherwise it kills you.
Other correction methods are also available.
Other correction methods are also available. That's
no. We are a single church.
Bonferroni is mathematically more conservative than the others.
Isn't that the problem though? It's very conservative, isn't it?
No, it's not. It's fine.
Are we going to explain Bonferroni for anyone that didn't Google it?
You just divide it. So you do the reverse of the math that Sam was showing you earlier with the taking something to the power of 7. You basically divide back out the number of tests that you've done so that you end up with the original probability.
Yeah, it's what number do you need to raise to the power of, in this case, 7, in order to get 95% overall, and it ends up being like 98 point something, probably.
Yeah. And that gets you back effectively the same 95% probability that you were looking for.
I seem to remember an equation with n-1 or something like that.
Yeah, and the point isn't that everyone should know how to do a Bonferroni correction off the top of their head. The point is that
it looked pretty simple when I Googled it.
Yeah,
it is. It's very, and that's the thing is I think it's very simple math. It's easily look upable. What's more important as the takeaway is that it can be applied if you know the number of examples. So let's say we do a Bonferroni correction here, and we are like, okay, yeah, we're there's nothing significant here, right? Walk away. And then Andrew is like, okay, but what about if we look at whether it works better on red products versus blue products versus, etc. And now we get into a problem, which is that in theory, you can keep doing this as long as you want and keep applying Bonferroni corrections.
Well,
Okay.
yeah, but
And obviously, if you've got like a 5 out of every 100 tests is going to give you a significant result just by chance, if you do lots of them.
Effectively, what you end up doing is saying, like, you're conceptually a bit at risk of saying that you're going to do an infinite number of tests. And then the math doesn't work anymore.
So there is a way to do it, but it starts getting really, really tricky.
Yeah.
Which is essentially, you know how you can do an infinite sum that comes to a...
Sam, no one understands.
Okay.
There's something
Tell me,
about
what
a hotel and infinite beds and stuff like that. That's all I remember about infinity. So.
Okay. If you add a half plus a quarter plus an eighth plus a 16th plus a 32th plus a 64th and so on into infinity, what does that add up to?
Never gets to 1, does it?
It
should get to 1. Okay, in infinity, yeah, it should be 1.
Gets to 1. You can basically do the same thing but with Bonferroni correction. So if you want 95% overall, the first test you do is 97.5, i.e. 1 minus
the threshold you have to now hit in order to...
1 minus 2.5, and then it becomes 1 minus 2.5 over 2, and then over 4, and then over 8 and 16 and 32 and 64 and so on. But what happens is, because every time you test, like the sum total of that thing will end up being 95% if you keep testing into infinity. But every time you do a test, the next test gets harder in order to compensate for the fact you're going to keep testing until you get a significant result.
And what's really weird conceptually is that, like, because you guys might be thinking, like, oh, like the color thing, we should test that, but stupidly we did the clothes first and now the second one is harder. And like it's a weird, like, it's almost like a sort of like a Schrodinger's cat type thing.
Yeah. Why does the order matter? But the order matters because you'll stop as soon as you get a significant result.
Exactly.
So actually it does matter the order that came in. If you did the color before you did the product, you maybe never would have done the product.
Yeah.
So actually order matters.
And
so if you
we should say, as I was going to say, we should say as an aside that actually mathematically, the same way that we correct for multiple tests in this case, it's the same way that we correct for the peaking early problem. It's conceptually it's the same thing. It's running multiple tests. So Bonferroni correction is basically the answer.
Yes, it's always the answer. But speaking of stopping early, Nicola has made a good point in the comments that medical experiments often stop early if it looks like an intervention might be causing harm.
Or indeed, if it looks like it's so good that it's a problem to withhold it from other people.
Exactly.
Well, that's it. So there's and I think that was the case in certainly one of the vaccines was actually this looks like this is so strong, rather than wait and allow hundreds of thousands more people to catch the virus. We're going to stop early so that we can start production. That again uses exactly the same methods. Like if you're running through it, you should be doing a Bonferroni correction as you're running through and just testing it in series.
And that's a good reason because of that ethical decision making that is happening in medicine. That's a really good reason for them to set up the experiment to allow for early peaking, so that they can and AKA to be applying these Bonferroni corrections, so that they can be making saving lives.
And also, I was also going to say if there's also the possibility of the two things. So in this case, we talk about also causing harm. Actually, if that's in theory, the causing harm is independent of any beneficial effects that the drug might cause, and so you can run those as two completely separate experiments, same populations, but you don't have to consider the statistics of one and the number of tests and the threshold within one to go to the other. And so for the medicine, it might be actually you've got quite a high threshold because there's already good products to treat this particular disease, and so you need a strong effect size. And so you set a high bar for that. But actually, when it comes down to, are we hurting people, which obviously is a bad thing, you can set a very low threshold and be like,
you might be more willing to be wrong about hurting someone than you are willing to be wrong about providing a beneficial treatment.
Yeah. So it might well be that you have 99% for treatment, 75-80% for harm, and you just go, okay, no, we're hurting people, pull it out, end the experiment.
One interesting thing. So when I do experiments at work, we allow for early peaking, and which means that and we have an agreed upon threshold about when we'd like to roll out an experiment, and fairly typically for online websites, the threshold is 90%. So we're willing to be wrong one time in 10 because no one's going to die. The risk of harm is very, very low. And so it's better to make the trade-off to make a decision more quickly than it is to keep running the experiment. And sometimes it's a little bit more complex than this. Like we're looking at a single number. There could be multiple numbers that we might be looking at. We might be looking at not just the people who click on the button, but maybe the people that complete the purchase, for example, right? And what if those two numbers tell us conflicting things? Or one is still ambiguous and the other is looking like it meets our threshold. And I make the same sort of medical experiment at work sometimes. I will say is that if we have significant evidence of a benefit, we should not withhold that benefit from the other 50% of the population. And that it's better to do that than it is to wait to measure things more precisely. That we have to make that trade-off between making the decision versus understanding something for the sake of understanding something.
And I think there might be one more thing that we might want to touch on.
I was just going to say one last takeaway that I have on this kind of multiple testing example is that what I recommend people do is think about the potential multiple tests that they might like to do ahead of time, and especially come up with a reasonable hypothesis for why there might be variation across that segment, that metric. So I think that in this example of where we're looking at color changes on a button that depend on product type, why on earth would it be different for clothes versus food? We have no a priori reason for thinking that would be significant.
So however, is this where pre-registration comes in?
Yes, exactly. So this is where we might set it up ahead of time and say, these are the comparisons that we're going to look at in our methodology. And I think that's really useful because it avoids you getting distracted by, but this one thing was statistically significant, even with our Bonferroni correction.
Yeah.
Because there's still a chance that you're wrong with that, right? All it does is it stops compounding the odds of being wrong, but it doesn't actually prevent you from being wrong. And so, I think the color-based example, where I suggested that maybe the button could have different effects depending on the color of the product, to me, that does sound like a plausible way of segmenting or subdividing the data, because it might be reasonable to assume that maybe the button doesn't stand out for red products, but it does for others, hypothetically. So, if we were talking about setting up this experiment ahead of time, I would say ignore this. And instead look at the color-based one. Can you think of another example that either would be meaningless or perhaps meaningful to look at, another dimension?
Price,
my brain is broke.
What was that, Sam?
Price.
Yeah.
So maybe
would that be meaningless or meaningful?
Meaningful. So cheerful little oh, hey, spend £2 on a new hair tie. If you're already maybe buying something else, maybe go, yeah, okay. Something that just brings it to your attention might well
Okay.
guide
Yeah.
sales, whereas expensive stuff you need to be more considered and thoughtful.
I think that's a reasonable hypothesis. I was thinking also maybe like region, the geographic region, like let's say this website, is international. Some cultures have like, really positive associations with the color red.
Yeah.
So maybe the button is more likely to work there.
If they're an accountant, they might think in the red and in the black.
Hey, yeah. If there was a way of knowing whether somebody visiting the website was an accountant, but maybe if you were selling like calculators and like accounting products, that would
along
work.
with our popcorn and shoes.
Mila, she's got weird tastes.
Cover everything.
But those are like, and that's the kind of discussion you'd want to have ahead of time before you set the experiment going. Is what are the possible ways we think that we might see significant effects if we subdivide the data, and like you say, pre-register that, which is what the sort of scientific and medical community is doing increasingly to avoid these problems around p hacking. And Sam, you were going to go with one last example.
Yeah. So the last one is, and this one is something that the all trials pre-registering and methodology approach will prevent, but is a bit of an issue, I think, at the moment, certainly with some pharmaceutical companies in the past, as well as proponents of pseudoscience like climate change denial. So Andrew has ousted Chris, or
freedom,
or maybe Chris has gone on a really long holiday.
Chris has gone on a long holiday. It's his turn.
And so
Andrew went crazy.
Andrew, what have you done?
Andrew runs the experiment. He doesn't like the results. He ends it. And then he runs it again. And then again, and then again. And he ends up running it 20 times until finally it produces a result. After 20 inconclusive results, it goes, yep, you know what? Red is better. And so in addition to testing multiple things within an experiment, in addition to testing the actual experiment itself multiple times, what we can do is just go, nah, forget about it. I'm just going to keep running again until I get a result that is positive, and and then just publish that one. Just make that one aware. So Chris comes back.
Is this the file draw problem?
So exactly.
Right.
So he doesn't tell Chris when he comes back. About the other 19
the first 20 tests, ignore them. Hey, Chris, we had a successful test. Red is better than black. Here you go. Bosh. And he's like, hang on, I've been away for like 4 years. This is 80 days.
I wondered why you kept extending my holiday.
But also, in particular, as well, actually, in the particular example that turned out, so this is I just ran the thing we had in the background because it uses a random number generator. It actually briefly ticked over and was significant for black before ending up being significant for red. And so optimal stopping, like if you're stopping it partway through, bosh, black, done, can it, end the result, end the experiment, start a new one, because motivated reasoning, and then, but actually, it did eventually.
So is this the one time in 20 that was wrong?
Yeah. Well, 21 in this case, but yes.
Yeah.
So even if you do all of the okay, here are all my corrections. Here's my methodology. Here's how I'm going to remove my outliers. All of those things that are good practice. If you then just refuse to accept the result and keep testing until you get a positive result, that's still bad science.
Yeah.
And still p hacking.
And I think one of the problems that people face in science is that pressure to publish and that idea that your career depends on you showing a significant result for an experiment that you've been invested in for a long time. And I think that what's happening in science more recently, like things around pre-registering tests to remove, because one of the things that pre-registering tests does is it, first of all, it removes a lot of that p-hacking that sort of multiple testing problem, but it also gives people a venue to publish, even if their results are not statistically significant. And the phrase that we use at work a lot is a negative result is still a learning, or a result that is inconclusive. You still learn something. And we think of it more as the goal. All research leads to an increase of knowledge, but it's a lot easier to say that when your job doesn't depend on the number of quote unquote like statistically positive results or significant results you get.
Well, and one good metric, well not metric, way of sort of ferreting out bad studies is to repeat them, as Sheldon said in the comments. Is actually repetition studies are really, really valuable. And in theory, you could do them on all results, but particularly if you're, particularly I suppose on the positive ones.
And I would guess so the phrase reproducibility crisis has been used in science for the last few years. This idea that actually when people have had funding to do to attempt to reproduce famous scientific experiments, and to look at that even in a more systematic way, what one would expect to see, which is 1 in 20 not being, not actually passing the redone test, is more like 1 in 3, or.
So this was Erika and I, when we were discussing like how we were going to do this, I kind of went, I want to end on this bit, and she's like, okay, what would that really show? This is exactly what it will show.
Oh, go on.
Okay. So you've got two different sets of results. This isn't. I'm going to move on to a different tab because that's just going to keep updating itself. It's going to be very annoying. So you've got true theories and false theories, and the true theories, they both going to use 95%. And so in the true theories, 1 in 20 is going to be falsely negative. Okay. So the total number of successes is going to be 0.95 times number of trials. And then the false ones, of course, 95% significance. Actually, 5% of them will slip through just as random error. Okay, so you get 5%. 5% there. Well, actually, if let's say that half and half of your theories are half of your theories are true and half of them are false. Actually, of the total number of 50 that end up passing through, the vast bulk, 47.5 theories, that our mathematical tests say are true. So the vast bulk. And so if we went away and did a reproducibility study, yes, you'd still end up with some false positives and some false negatives, but on the whole, it would be relatively accurate. But what if you have 100 false theories for every true theory? Well, actually, the bulk of your positives
are now false.
Are actually false.
False positives.
And that is assuming 95%. And with p-hacking, it's not 95%, it's less. And so this 5% left over, maybe it isn't 5%, maybe it's 10%, maybe it's 30%. And so that's because we don't know. We don't know beforehand whether they're true or false. We don't know genuinely. We can only work off of the trials, off the test.
And so that's how when you combine that effect plus p-hacking, that's how we can go from what we would expect to see in the literature, which is 1 in 20 failing reproducibility, to more like 1 in 3. And that's why I'm not a scientist anymore.
Okay, so that was Sam's ending. Are we going to run the discussion again with Erika's ending? And
so we're going to repeat the experiment, and you guys are going to tell me which one you prefer. No, I think that was everything we wanted to say. You guys were thank you. You guys were great participants.
So the important question is, do we change the buttons?
No.
Okay.
No,
Money
in fact,
get
I
up the
feel like you
drain.
should look at your overall website design and perhaps your product assortment.
Yeah.
Like you are all over the shop there. Just pick a category and go with that.
And Sheila's
And fix Sheila's diet.
Send Sheila to a doctor. Stop taking such long holidays. Don't quit your day jobs, guys.
Oh, right. Yes. So, right. With that in mind, what have we got coming up next time? So, next time is a little bit of an odd one. We're not going to be doing it on the Tuesday as per normal. And that's because we're going to be talking to Dr. John Cook about the Flick model again and climate change. And he's over in Australia. So, we've had to play around with the time a bit. So, we're going to be doing it on.
Because Australia's not real, right?
Yes, exactly. Yeah, exactly. It makes it so much different. And so we are going to be doing it on Saturday the 7th of May at 9:30 in the morning, which I think is 6:30 in the evening his time. And yeah, that should be really interesting. So yeah, please join us for that if you can. And
go back and rewatch our Flick video before.
Yes,
then.
we'll rewatch our one so you know what's coming up. And
leave comments and click like and
do all that lot.
Sign up to our Discord and our OnlyFans and whatever else we got.
Goodness. Nobody wants that. Oh my gosh. And on that bombshell.
Sam's like,
Keep it on, Sam.
Right.
Bye.
Bye.